To complete the structural qualification test campaign for NASA's Space Launch System, SLS, rocket, the liquid oxygen structural test article was pushed beyond its limits until it broke and water gushed from the tank. The tank is a test article that is identical to tanks that are part of the SLS core stage that will produce 2 million pounds of thrust to help launch the rocket on the Artemis missions to the moon. The tank was bolted into a massive steel ring at the base of Test Stand 4697 at NASA's Marshall Space Flight Center in Huntsville, Alabama. Hydraulic cylinders were then calibrated and positioned along the tank to apply millions of pounds of crippling force from all sides while engineers measured and recorded the effects of the launch and flight forces. For the test, water used to simulate the liquid oxygen flows out of the tank after it ruptures. The structural test campaign was conducted on the rocket to ensure the SLS rocket structure can endure the rigors of launch and safely send astronauts to the moon on the Artemis missions.
The Space Launch System's core stage is the framework of the world's most powerful rocket. But before it's assembled and integrated into SLS, the core stage's 5 sections will need a combination of more than 750 sensors, 45 miles of cabling, and 100,000 fasteners. All that work is being done as we speak. Let's take a closer look. At the base of the core stage sits the engine section, home to the 4 RS-25 engines, the thrust structure they push against, as well as more than 18 miles of cables. Because of this section's complexity and the extreme temperatures and vibrations it will experience, nearly 500 sensors are being installed in the engine section to monitor conditions. The core stage contains 2 separate fuel sources, the liquid hydrogen tank and the liquid oxygen tank. Together, they hold a combination of 733,000 gallons of propellant. This fuel is kept so cold that it will actually shrink the tanks up to 6 inches in length and more than 1 inch in diameter before they expand again as the fuel empties. That means that anything attached to the tanks must be secured with a variety of flexible or accordion-like or telescoping connectors. The intertank is designed to connect the 2 fuel tanks. It isn't being welded together like the rest of SLS. The intertank is being put together by 14,500 custom bolts, fasteners, and fittings. The brain of SLS is in its forward skirt section. The 45 miles of cables controlling the SLS eventually lead to the forward skirt section, where 3 flight computers monitor more than 1,100 sensors to ensure a successful flight. Power for the computers and other core stage electronics is provided by 4 lithium-ion batteries. Each is about the size of an average car battery and provides about 1.8 kilowatts of power for the rocket's 10-minute mission. NASA engineers are working hard as we speak to make sure that every part of the core stage is outfitted and tested. But that's just the beginning. Once the individual sections are complete, the whole thing needs to be assembled. But we'll save that for another time. Thanks for watching.
Within the SLS Advanced Development Office, we're focusing on a 130 metric ton vehicle that will take us to Mars. Now, the next thought is, with that particular vehicle, what enhancements could be done? This particular one is a smaller, compact diffuser. And through the development and test, we're trying to see if it would prove out to give us the performance that we're looking for, but also in a smaller, lighter weight package.
We're building this prototype as a potential add-on for the Space Launch System, SLS, which is going to be one of the largest rockets ever built. And when you do that, there's lots of things you have to consider. One of the things that you have to consider is the fact that the engines that are burning to propel this thing into orbit requires a lot of fuel. And so the large tanks that we have that store the fuel and supply it to the engines have to be drained very rapidly. And in doing that, that is really no different than taking a water bottle and turning it upside down and letting the water drain out of it. If you just turn it upside down, it wouldn't come out nice and smooth. So what we have to do is introduce gas into the empty space to fill the void left by the liquid. So that's called pressurization of the tanks. In order to do that, the gases would come in at a very high rate of speed, actually about 1/3 the speed of sound, if you just had a pipe to inject it into the top of the tank. What we want to do with a diffuser is we want to take that high velocity gas that normally would impinge on the liquid surface and turn it into a horizontal flow that will help prevent the jet from impinging on the liquid surface. We have a workhorse prototype diffuser to test out the concept. While we're testing the diffuser, we're taking lots of velocity measurements and gathering a lot of data in order to determine whether our computational fluid dynamics models accurately predicted the behavior of the diffuser relative to what we're actually seeing in test.
When you're building a system as complex as SLS, there are a lot of things you have to think about. The problem that we plan to address is called geysering.
One of the first things that we have to get our arms around is how we load the vehicle with cryogenic propellants and how we safely load the vehicle. Geysering happens whenever heat is entered into the system and a large bubble forms and it displaces liquid and allows that liquid to come crashing back down and cause a hammering effect on the system. And this hammering effect can damage the tank or the feed lines or other components. So we put together a full-scale test bed here at Marshall that simulates the LO2 feed system for core stage.
We're utilizing Testan 4670 at Marshall. We've set a tank that Boeing procured, which is representative of the SLS height, and we've got full-scale feed lines where we've matched geometry to the SLS flight LOX feed system. We plan to mitigate the risk of geysering with circulation induced by helium injection. We've got 2 feed lines which feed 4 engines. The 2 feed lines are connected via a 4-inch crossover. We've got 2 helium injection ports. Helium injection will induce circulation up one feed line. Cold, fresh LOX from the LOX tank will flow down the other feed line and across the crossover into the other feed line. And the circulation will prevent a stagnant system and therefore prevent geysers.
Anti-geyser is one of many development tests that we have in series that help us to ensure a successful maiden flight for SLS that we're very much looking forward to.
So we were tasked with essentially loading the largest launch vehicle ever built by NASA in history safely with liquid oxygen.
We started planning this test program about 3 years ago. We started by doing a water development test, and we learned a lot in that test.
This is the first time that we've built a test article just like this. It's very unique to any other LOX system on a launch vehicle ever built. It's different than Saturn, it's different than Delta, it's different than Shuttle, and so there's a lot of unique things we needed to learn.
Today was our 12th day of testing. We have a total of around 20 test days for our entire test program.
The test program was designed to make sure that we had all of the possibilities, all the variables enveloped, things like ambient temperatures, failures of bleed valves on the engines, failures of helium injection, facility failures where we lose supply of liquid oxygen. We've spent a lot of time in that realm and failing certain things that could fail and make sure that we have the right control knobs on and in place to maintain the system's safety. The timeline to fill a vehicle this size is on the order of 3 or 4 hours. Once it's filled, we'll sit for a number of hours for things like waiting for the system to actually stabilize, waiting for astronauts to board, and other subsystems to get ready. Once you get closer to launch time, there's about a 10-minute window where you go into your launch countdown, and that's when you're closing off the subsystems from the facility, isolating them. So this test program really demonstrates every little step along that entire timeline to make sure that we have a good understanding of the system behavior, that everything's safe.
And that's what building a rocket is all about, is taking all of those complex pieces, putting them all together, and being able to then go test our operations to have a successful launch of the largest rocket that's ever been built.
The SLS program office here at Marshall is a very lean organization. It's very flat. It's managed by a very good mix of managers who have early vehicle design experience as well as flight operations experience. We have people within our management team that even worked in the EVA office at JSC. So there's a really good blend of personnel and experiences that help us take SLS forward in a very affordable way as we transition from early development and design into production and flight operations in 2018. That organization has been very stable throughout the 5 years of the program. It's very flat with a level 2 function, which is the primary program, and a level 3 function, which is all of the hardware elements that manage the program. That organizational structure has remained very stable. It being lean and small, it's very agile and has a good ability to respond to issues of the day as well as make timely decisions, which was a big lesson learned coming out of some of the earlier programs. It's lean, small, agile organizations tend to respond quicker and they make more timely decisions. So that was one of the primary drivers behind the way SLS is organized at the program level. Within that, we have matrixed in, is what we call it, but for all intents and purposes, we're all embedded. It's one large program between the program people, the chief engineer's office, chief safety office. We're all represented in that SLS program managers as one team. So all three legs of the traditional governance model are represented in a small, lean organization. Within the SLS program structure today, all three legs of the governance model are represented. That's safety and mission assurance, engineering, technical rigor, and program, which is primarily the programmatic and management aspects of the program. Those three functions, although independent, are embedded in the organization. We share the same office space. We really live and breathe as a single team. We're involved in all the same meetings together. Every function is represented at almost every meeting that we have. So as issues boil up, things that need to be resolved, discussion points, decisions about approach, those decisions are able to get vetted and decisions made very quickly because all those players are involved from the beginning. Issues that need to be adjudicated get elevated up through control boards. We have engineering control boards. There's a safety and mission assurance equivalent. There are also programmatic boards where cost and schedule issues are decided. So there's a defined structure and path for issues to be elevated for decisions when those decisions are necessary.